we'll do some fine tuning of we'll do some tuning on LLMs and some deployment stuff. So you get to deploy a model across multiple GPUs. So you'll understand exactly how that works in practice. But we won't be touching RAG in this course. We have some other courses coming up on that. Very good question. Okay, but why is there this trend happening towards larger and larger models? This particular figure is taken from a paper called Deep Learning Scaling is Predictable. So they looked at different factors that improved neural network performance. So if you really look at it, it's showcasing that as the training data size increases, you can expect a significant decrease in your generalization error of whatever network that you're training. And everyone's like, okay, let's just scale up our training data size and everything will be good. But what's the main challenge that we have? If you've ever done any type of data labeling, humans are not cheap when it comes to data labeling. Even if you go to a different region in the world, at scale, they're still not cheap. And every single large machine learning company is going after data annotation. And I just saw a really interesting post from an engineer at OpenAI, and he was saying that hyperparameter tuning actually is not necessary. It all comes down to your data. And this is something that he observed across working a number of different models that he had trained inside of OpenAI. So just wanted to share that as well. But as we try to get, come back to this curve, as we try to get closer to that irreducible error, we need more and more training data, and that cost is just going to be way too high. Here's an example of maybe why this problem is difficult. It is time consuming. So on the left, you see for self-driving cars, we start off with, let's say, tens of petabytes of data collected from all of the cars. Let's say you have 1,500 people to label 1 million images per month. And then on the right-hand side, we show a slightly different task where you require a significant amount of expertise in order to label some of this data. And you can see there are only about 3,000 radiologists in England. So if I had to hire them to label petabytes of data, it actually won't be very feasible. So here comes unsupervised learning. And the idea here is you can have a large corpus of data, not necessarily framed or explicitly labeled, and then you can actually train some of these models on that. And in NLP, this is from a paper called, let me see which name is it. Yeah, Scaling Laws for Autoregressive Generative Modeling. But the idea here is folks observe that if you increase you can't just increase your data size, you have to increase your compute, the actual size of the network, and the data correspondingly in order to see an increase in performance. And in this case, an increase in performance is just a reduction in your test loss value. And if you're able to do that, this is why folks are trying to build larger and larger models. This is just another excerpt from, I think, Scaling Vision Transformers. And the idea here is to show that these types of scaling laws apply across many different domains. So this is computer vision. And then I think this next one is from speech. So this is a paper called Scaling Laws for Acoustic Models. And they're showing that with an increase in compute, you see a corresponding reduction, in this case, in the L1 loss for different types of models. And here's one for, let's see, image to image, text to text. And it's showing that this law applies across different domains as well. Petabyte scale, technically, you'll have folks at petabyte scale, but I think they measure it, at least in NLP, folks will measure in terms of number of tokens. So trillions of tokens is more the standard now at the bleeding edge, and I would imagine higher numbers of trillions of tokens. And one interesting thing about when you go to train on 1 trillion tokens, and we'll get into training as we move along in the course, is that you don't necessarily actually do many epochs. You end up just doing one epoch of training. So one pass through the entire data versus if you had trained other models before, you would have had many different runs through your training data because that training data is so large. Okay? But let's talk about the cost. So in this chart, we're showing, hey, for some exponential increase in compute, we get essentially some marginal decrease in test loss. And is that marginal decrease in test loss worth all of this actual extra investments, right? So you're seeing a 10,000x increase in compute gets you maybe 2 or 3 points reduction in your test loss. So I know you might be wondering, okay, this is too expensive, we're not doing this. But the true reason why people are going after this is something called emergent abilities. It's going beyond accuracy. It's in line with few-shot learning and zero-shot learning. And this chart, I think, kind of describes it fairly well. So on the x-axis, you have the amount of training data, and on the y-axis, you have the corresponding accuracy. So what we're trying to show is that with more training data, you should hopefully get something more accurate. And then the curves actually represent the model architectures of increasing model size. So we have a 1.3, a 13 billion parameter model, and a 175 billion. Note that these curves, these are some older papers as well. There's a lot more new information that has come out now, still supporting the same paradigm. So the x-axis, like I was saying, is showing number of training examples ranging from 10 up to, let's say, 100 or 1,000. And if you can see the smaller models shown in green and orange, they're not able to learn as well with a large amount of training data versus a large model. And I give it a little bit of training data. So the large model is shown on the blue curve. That model is able to learn a lot faster with a lot less data. So think about it. It's very expensive to get a ton of training data. What's the size of this training data set? In this case, we're just using 10 examples, right? So 10 to the 0, 1 to the 0 is 1. This is actually a single example, so that's a single shot. We're teaching this thing. So this is the idea. Given, and I know many of you would have used ChatGPT by this point or some other large language model, and given a single example, you can get it to do a particular task. So this is the truly the thing that everyone is going after, not necessarily sort of a bigger model, but this notion of completing tasks that a model was not explicitly trained to work on. Okay? Here's an example of prompt engineering. Honestly, this is supposed to be a video. I don't personally have the video on my side, but what it shows is that you're giving a few examples of English to French pairs. I think in this model, it was not explicitly trained to translate from one language to another, but because it's sort of seen very large text data sets across the internet, it inherently has learned to do translation, right? Let's talk about prompt design. So in this chart, we're showing different strategies for increasing the performance on the glue benchmark from model tuning versus prompt design. And on the blue curve, you can see that prompt design was not necessarily performing as well versus traditional models like prompt tuning. So prompt tuning is showing a lot of performance. You don't need as much training data as you might have done with fine tuning, let's say on BERT and things like that. And you're able to get a lot better performance. Implications of software. I think this is fairly straightforward for almost all of us here. There are tons more companies that are coming in now. If you're in the venture space or the investing space, I find it very interesting just because it can be very hard to distinguish what's a good machine learning company versus not, especially those that have been built on ChatGPT. And given their latest image release, I think a lot of startups are not necessarily around. This particular demo would have shown Toy Jensen speaking and responding to different questions. And the idea there is to show an agglomeration of a bunch of different models, speech to text, text to speech, having a RAG system as someone asked behind, and all of that coming into a single avatar experience. And we'll learn about Nemo Megatron and the Nemo package from NVIDIA, and this is what we use to distribute to get really high performance from training different models. This was another example of using just voice commands to control this particular experience where you would actually take different views of the car and do different actions inside of this program. And this particular example is just showing question answering and sequence summarization. So many different examples of where large language models are being used to either generate new text or summarize things. It's affecting search, it's affecting e-commerce, it's affecting almost every single industry. And I see we have some good discussions going on in the chat. Give me 1 second here. And in terms of data sets, lots of different people are releasing very interesting data sets every day. And in this particular video, sorry that I'm not necessarily showing the video, now we're asking a robot to actually take actions from a large language model to perform a different set of tasks. So the task would be, can you bring this Coke can from this table over to another table, and then all of the sequence of actions in between that time to instruct this robot are generated by a large language model. And we're seeing a lot of progress on that from Google and other companies. Here's an example for computer vision. In the image on the left, we see a prompt to do image annotation through completion. So essentially, we're able to figure out, hey, this guy's cutting a log, et cetera, and we're identifying certain things in the image. And then on the right-hand side, the model understands the context of this particular image, and that X is actually marking something of significance. In this case, it's a treasure, some treasure in a pirate map, et cetera, et cetera. So you're seeing that a lot of these large neural networks go beyond sort of predicting the next word, and they're able to apply in many different domains. I'm sure everyone has generated some cool images. I'm a big fan of Midjourney. And depending on what you're doing in industry, you might run into legal issues when it comes to having some of these models trained on open data versus proprietary licensed data. So we have a project at NVIDIA called NVIDIA Picasso. So we've partnered with Getty and other large image houses to license their data, and the corresponding artists get paid for the information, for their data that was used to train these different models. Going beyond this, this is just a bunch of different papers that you can reference when it comes to seeing these types of large language models or large deep neural networks applied in different domains. So here's a paper showing for automatic applied to speech recognition. There's another one for chemistry. And all of this comes into looking at your data as a sequence and then completing a sequence given, a particular prompt or given a particular instruction. And in this one in biology, you're looking at different strings of chemical structures and looking at that as a sequence and then seeing how can you then match sequences or come up with new sequences in order to solve different problems. So hopefully that gives some context as to maybe why large models taking one step back. People are very interested in the emergent abilities. So as I scale up, these things can do things that I didn't explicitly train them to do, and I can just feed them a ton of data. Naturally, for different domains, you'll have to sort of fine tune and align that data for a specific task, and there's lots of things out there to do that. So here's the fundamental shift, sort of encapsulating what we said before. The old way on the left was you would require a significant amount of label training data, so input-output pairs, and that would have come with a lot of costs and sometimes privacy issues, especially the harder, more specific the domain. You would have to, actually hire very smart people or very specialized people in order to do it. And then on the right-hand side, I don't necessarily need label training data. I take all of the text on the internet and I look at that next token prediction or their different training schemes, and I can now leverage these large data sets in order to create this notion of intelligence of completing a sequence of words. But that is a lot more computationally expensive than what was there before. But to justify that, you get these emergent abilities. So what we're seeing now, so instead of training a small model to solve a specific task, we're now going to train a very large model and then use prompts to actually solve specific tasks. And in some cases, we'll do things like prompt tuning, et cetera, et cetera. Okay, so what are some of the challenges, right? The first is time. Here's That's actually truly the main reason why people are scaling up their training. Um, this particular equation is showing an estimate for the number of floating point operations you'll need per iteration to train a large language model. And it's in terms of the number of layers, your sequence length, the vocabulary size, etc. And the larger number of floating point operations you have, that means you need essentially a larger, compute environment in order to finish training this model in reasonable time. Let's take an example. If you were to train a 1.7, excuse me, I think it's 1.7 billion. Yeah. So if we were to train a 1.7 billion parameter model, so we're looking at the first row, it would take 6 weeks on a single DGX A100 system. So a DGX has 8 A100s, and 2 weeks with 4 of these systems, totaling 32 GPUs. But now, if you start to scale that up to 145 billion parameters, you need 65 weeks on a single DGX system, or 1 year on 4 DGX systems. So imagine you are trying to create this very competitive large language model in the world, and you have to wait an entire year. But what if during that training run, you had to restart it a couple of times because you weren't converging? Depending on your training data, you might have to clean your training data again. So you would have had all of these different restarts, and every time you kick off, it'll take you a year to converge. It's not necessarily feasible. So what a lot of people are doing now is scaling up these systems. So now within a month to 2 months, I can get an answer. I heard some interesting anecdotes about um, Gemini's, Google's model for training, and it'll take them, I think, probably about 3 months to train on an enormously large amount of compute. So you can see why scaling up this compute is very important, because I think if they didn't have as much compute, it would have taken years for them to train a real model, a really useful model that's competitive against what's out there. This chart is showing the effect on training loss with respect to the number of parameters. So the good news is that you can end up estimating a lot of papers now, and a lot of these large training teams can actually estimate, um, given a particular compute budget and a particular size of model, what sort of accuracy that you might be able to get from different types of training. I see Renan said, hey, the more you buy, the more you save. And that's not necessarily a sales gimmick. It's actually true. You are compressing the time. In addition, as you think about one big shift that's happening in industry, is this shift when it comes to leveraging power. So the amount of compute that you have per wattage of power is becoming very important, especially as different data centers are becoming power limited. I was just talking to a friend who builds data centers, and basically a lot of cities are not giving current data centers extra power capacity with which to expand. So if you can't expand by power, you now have to expand on a compute basis. So you're getting more compute per unit energy. In this particular slide, this is just showing you see an increase in performance as you apply this notion of scale of compute and the number of parameters of models. So it's very interesting that you see this happening across all different domains. Okay, in terms of challenges, we mentioned that time was a major one, but what are the different aspects of model training at scale that really affect the time? So if we look, you need effective tools to manage hardware, actually very effective algorithms to maximize the hardware itself. So the hardware layer, the software on top of it, and then the actual interconnects between these, all of those play a significant role in training cost and training time. In terms of algorithms, everyone's probably familiar with the transformer model if you're taking this class. But what ends up happening is people don't necessarily use a vanilla transformer implementation. There are a lot more optimized versions of the transformer model. You can apply different activation functions, nonlinearities, layer normalizations at different points. You can end up changing the precision to affect the training stability as well. So for instance, why a lot of people like the H100 GPUs is that you can actually do training in FP8. So instead of doing training in 32-bit precision or 16, you can now go down to FP8 because there's actual both hardware and software accelerations to achieve better training performance. This chart, you'll see this quite a lot during the class, and it will become a lot more transparent as to what's happening. So we'll be talking about things such as tensor parallelism, pipeline parallelism, data parallelism. But the main idea is how do you now take a very large model with a bunch of different layers and now split it across different accelerators. And we'll come back to this slide coming up. Okay. All right, so here's some of the state-of-the-art libraries that you might be able to leverage when it comes to training at scale. If you are going to train at scale, for the most part, Reed, I think FP8 is only possible with H100. That's to the best of my knowledge at this point. But I'm happy for someone to fact check me on that one. Okay, so DeepSpeed is from Microsoft. DeepSpeed is a very popular package. You'll be using DeepSpeed today, so you'll get some hands-on experience with that. From PyTorch, there's fully sharded data parallel. So as you think about data parallel, instead of pushing different copies of instead of splitting your model across GPUs, you have different copies on each GPU, and then you're just passing different pieces of data, and then you're synchronizing weights. We'll talk more about that. Nemo Megatron from NVIDIA. So we were one of the first ones to really show how to scale up this type of training. So we trained like a 530 billion parameter model on NVIDIA GPUs, and that particular paradigm for tensor and pipeline parallelism, as you'll learn here, was one of the things that enabled folks to really start scaling out training. Fairscale is from Facebook, and Apex is another NVIDIA project to do mixed precision training. Okay, let's just take a quick look at some systems. I would technically say this is an old system. So this is showing a picture of DGX A100 SuperPod. I think, I don't know how many GPUs are in this, like at least 1,000 and something GPUs. It's usually at least 20 nodes. So 20 by 8, I think. So you'll have a DGX system, and then you'll just basically replicate them into what's called a SuperPod. But DGX A100, that's old news. Now you're seeing DGX H100, these large compute systems. And here's some of the different places that have them. I have a friend who's at University of Florida, and he trains some very large models. So I get to vicariously live through him. Not everyone gets to kick off these large training runs. I got to interview a product manager from Google, and basically I was just asking, what does it feel like to kick off these huge training runs that would run for months on a significant amount of compute? I think each training run can be up to like 5 million or more, depending on when you kick it off. And it's almost, I asked if it was like a nuclear bomb where everyone had to sort of sign off, and like 3 people had to hit the button at the same time. So that's my anecdote story. Facebook bought a huge cluster recently, and they were replacing their V100 clusters, and I believe they bought A100s, but I imagine that they'll be looking at H100s as well. Okay. Yep, so TII, I see some folks talking about TII. They were one of the first ones to release an open source language model, which I think really changed a lot of folks' minds. And then Falcon came out, and now you have things like Mistral. So there are lots of popular open source models coming out. And in the last lab, we'll end up doing some inference. Okay, let's talk about memory optimization. So in this example, we have a 1 billion parameter model that's trained in FP16 format. That means technically we can store 2 bytes per weight, 2 bytes per gradient, and then almost 12 bytes for the optimizer state from the Atom optimizer. So one of the things that was quite interesting is that the Atom optimizer, because you're trying to remember, all of machine learning is we have some error function, and we're trying to minimize that error function. So we're trying to find some direction, some amount of distance that we're going to travel along this function. and this function can have billions of parameters or billions of dimensions in order to optimize our error. And in order to effectively navigate this non-convex function, you end up needing like different things like momentum in order to best estimate what direction you should be going. Okay? So this is why you're seeing things like Atom Optimizer storing a lot of memory. Let's see what's the last thing I want to say here. Yeah, so 1 billion parameter is small. I said that you would see this slide again. So if you actually want to really understand what's going on here, this is showing two different transformer layers. So data parallelism means that these two layers transform. I don't know if you can see my mouse. Is my mouse flickering on your side? Sometimes that happens in this thing, but I hope it's not. Okay, perfect. So I can actually move my mouse and you can see. So I have two transformer layers. Essentially, this will be sitting on one GPU. Well, no, this will be sitting on one node. And then I'm splitting this model either directly through the model, splitting it in half, or then you can essentially split it in chunks where you see pipeline parallelism. We'll get more into that coming up soon. But I just wanted to continue to prime your mind as we go through this. Automatic mixed precision. This is just basically at different points. So if we see, if we start at 1, so my forward pass, I'm going to do a forward pass in FP16. I'm going to do my loss in FP32. So I'm very accurate. And then I'm going to try to scale that loss down to FP16. So you're seeing this modulation between different precisions throughout the entire training loop. And that's both a function of hardware and software optimizations that allow you to save one, the amount of data that you're sending in addition to the math intensity with which you're processing. Activation checkpointing is another trick that you see people use. So the goal here is at different points during your forward pass of your network, you'll need those output activations in order to compute the backward pass, right? So the backward pass is saying, how much does this particular parameter contribute to the error? And instead of actually storing these values for the backward pass, you can just recompute them when you actually need them at that time. So that ends up saving on your memory. So you'll see a lot of people with limit, especially with bounded compute, they'll just say, okay, I'm not saving a lot of stuff. I'll just recompute it because I have a limited amount of compute. And then offloading is another technique where you actually start putting your weights and stuff like that on CPU memory. It's where you tend to have, let's say, a much larger amount of memory, but that memory is a lot slower, and then you come into this, data copying issue. So writing to these types of storage or writing to CPU memory is not necessarily fast, and at scale, folks have no business writing to CPU memory in order to train in reasonable time. So Megatron LM is an open source project from NVIDIA that was really trying to push the boundaries of large scale training. We create the top GPUs and we're pushing these systems to the limit. So it's not necessarily us just selling these systems. We use these systems internally for our own research. So it's actually onus on us to optimize these systems to the best as possible because we're paying the exact same thing that everyone else is paying on the outside. Some of the things that came out of this are tensor parallelism and interleaved pipeline parallelism. We'll talk a bit more about that. And that's just how you're actually splitting up the model, a single model across multiple accelerators, right? Where a single model does not fit on a single GPU. And then Nemo Megatron allows you, this is a series of packages in addition to folks like experts and systems in order for you to actually do this type of training at scale. We're now calling it Nemo. So if you want to train large models like we do inside of NVIDIA, you can leverage some of these things. And you're able to pull a lot of these training recipes. But one of the most important things, I think, if any of you are thinking about doing large-scale training is there are a lot of lessons that you probably don't want to learn the hard way, right? So on the left-hand side, you'll see a bunch of different ways to distribute your model across different GPUs. In addition, you'll have training recipes for very specific types of models. If you're training your own GPT or another T5, you'll have different things like that. And then as you move your way all the way over to inference of these large language models is not cheap. So you have to, it's in your best interest to figure out how to best distribute these things across different GPUs. So to summarize, NeMo Megatron, this is for folks who are working production, and then Megatron LM is for folks who are doing bleeding edge, large scale training research. So, and we partner with a lot of different companies in this space. Okay, I think, yeah, let's take a look at what we're going to do in the lab. So we're going to try to simulate a huge cluster. We're not giving you a huge cluster. 3D parallelism, that's a good question. I'm not, for custom architectures, oftentimes when you end up starting to get into custom architectures, you'll end up using very defined training blocks, and you'll see in this class today, you'll actually play with the faster transformer backend, which is now turned into what's called TRT LLM. TensorRT is NVIDIA's model compilation package for essentially reading your model and figuring out the best way in order to implement it across a set of GPUs. And that's one way where you can deploy for inference, not necessarily for training. But coming back to the slide, you're going to get 4 A100 GPUs, and we're going to act as if they are two different nodes, and there are multiple GPUs inside of two different nodes. So you'll actually see how to apply some of these performance optimizations. Naturally, they don't necessarily mimic a huge cluster, but really want you to try to understand exactly how these things are being mapped across GPUs. Okay. And in the next lab, we'll look at distributed data parallel, tensor pipeline parallelism, and some of the different memory optimizations that you can use. Okay. So in the lab, let's go ahead and hit this launch button on this side, if you can still see me. So you're going to have 6 different labs that you can do. Your first lab is just, well, the first one is just if you don't know how to use Jupyter. I would hope that everyone does. And if not, just go through that lab. You're basically going to be hitting Shift Enter at different points. And then this particular lab will walk you through getting to use Slurm, in addition to how the actual hardware is configured. So one of the things as you read through this, you'll start to realize is the actual networking and the interconnects between GPUs. Every single thing on a system matters when it comes to performance. I see Ani joined late. So Ani, let me just copy things from notes, but go ahead and run through each of these labs, and we'll be online to answer any questions. Yes. Well, the notebook, some of the notebooks, there may be some verbiage in the notebook that says V100. Please point that out to us, right? Because we updated these notebooks from V100s to A100s, so we mightn't have caught all of the text. But you are using A100s under the hood. Yes. I see someone asked if the notebooks have been around since 2020. Yes. Yes, the NV link is set up automatically. If everyone work on labs 00 to lab 04, it says GPT language model pre-trainings optimizations. And then as you finish each lab, just put 01 or 02. So I just kind of know where everyone else is during the class. You have about an hour to run through these labs. And if folks finish faster, we can move on to the next section. There's usually, so I do recommend you right click on each notebook on the left hand side and you download them. But one other thing that I think comes up at the end of this lab is, hey, I want to completely replicate this environment and do these labs. That's not oftentimes possible just because these labs are designed and tuned to be deployed on the cloud. So if you literally just download all the code and you try to pull the container to run it, it doesn't necessarily run one to one. So I wouldn't necessarily expect that type of thing to work out of the box. So just wanted to level set on that.